and we'll mainly talk about the lower bound via a geometric approach. This is a joint work with Professor Ayfer Ozgur and Professor Tsachy Weissman at Stanford EE. So the problem setting is as follows. Suppose we have a parametric family statistical model P of theta, which is the default product distribution P theta 1 to P theta d. Then there are n sensors, each of which received one independent sample from P theta, that is x1 to xn. So note that x1 to xn are vectors. And each sensor can send k bits to a centralized processor, and then the centralized processor outputs an estimator theta hat, which for the vector theta. So in this problem, we have three parameters. So n is the number of sensors here, k is the number of bits, that is the communication constraint, and d is the dimensionality of the parameter theta. And we'd like to characterize the minimax mean squared error in estimating theta over all possible schemes, including all possible communication protocol and also the estimator theta hat. Let's first talk about our communication protocol. So a very simple protocol is that each sensor sends k bits independently of each other to a centralized processor. And actually, in this model, we consider a more complex one that is just the blackboard communication protocol. That is, there is a blackboard in front of the n sensors, and each sensor can write at most k bits on the blackboard. And when one sensor writes a bit on the blackboard, any other sensor can see it. So they can just act after they see what the previous sensor writes on the board. So this communication model protocol allows lots of cooperation, and we'd like to prove a lower bound for estimating theta. Okay, here is our main result. Actually, we establish a local minimax lower bound in this case. So fix any theta naught which in the parameter set, and let s of x to be a score function of the little model p theta around theta naught. That is just the partial derivative of the log likelihood function. Then, assuming mild regularity conditions, actually we have the following minimax bound. Recall that the variance of the score function is sufficient information. So the first bound is actually by some classical asymptotic statistics. So the bounds which are of interest actually are the latter two bounds. For example, the second term, compared with the first term, we have an additional d, factor of d on the numerator, but we have also an additional term 2 to the k on the denominator, which means that compared with the centralized performance, the second lower bound actually shows that we can do it up to a penalty like d over 2 to the k. And surprisingly, we also have a third lower bound, that is d squared over nk times the squared psi2 norm of the score function. So recall that the psi2 norm of a random variable is just the sub-Gaussian parameter of that random variable. So compared with the third term and the second term, we find that the dependence on k actually are different. But the dependence on the shape of the score function are also different. So actually, we have two distributed lower bounds here, and it seems that the dependence on k, for example, actually depends on the shape of the score function. Okay, let me show you some examples. So firstly, let's consider that the p theta is just a Gaussian location model, and we'd like to estimate the mean vector. Actually, it should be theta of this model. And in the centralized case, we know that the MSE is d over n, and there has been lots of work showing that actually in the distributed case, the MSE is d over n times d over k. So actually here we have a penalty term d over k. And let's also consider another model that is just a discrete distribution estimation, where we'd like to estimate the d-dimensional probability vector theta 1 to theta d. In this case, the centralized MSE is 1 over n, but the distributed MSE is 1 over n times d over 2 to the k. So both these bounds are tight for the respective models. And we see that actually here we have different dependence on k. Here is linear in k, and here is exponential in k. And actually, this is caused by the different nature of the score function. Let me show you a very specific example. Suppose we consider a product Bernoulli model. And in the first scenario, we assume that the mean of each coordinate actually lies between 0 and 1. And actually, I tell you that the distributed MSE actually up to a penalty d to the k compared to the centralized case. And if we add a new constraint, the sum of theta I equal to 1, actually, that is, each theta I is very centralized at 1 over d. Actually, the penalty term become another term, d over 2 to the k. So which means that even in the same statistical model, at different locations, actually the distributed MSE can be different. Actually, if we do some computation here, so for theta naught equal to 1/2 in the product Bernoulli model, the second term corresponds to variance is something like this. Yeah, the variance of a score function is a constant. The sub-Gaussian parameter is also a constant. So here, the second term actually is the leading term, while when theta naught is 1 over d, the variance of score function is d. The sub-Gaussian parameter actually is d squared. So in this case, this term becomes the leading term. Okay. Now let's just briefly talk about the proof techniques for this lower bound. So actually, our proof builds upon a very direct representation of our communication constraint. So actually, the main difficulty is to characterize the protocol. So this actually adopts a very well-known representation that is in the blackboard model. Let's say the red circle represents sensor 1, blue circle represents sensor 2, and the green circle represents sensor 3. In the blackboard communication model, firstly, we need to decide which sensor speaks first. So in this model, here the red sensor speaks first, and if it says 0, then the sensor 2 speaks next. And if the sensor 1 says 1, and then the sensor 3 says next. And how do each node decide which to send is just by some strategy function. We assume that it's deterministic, but yeah, here. So actually, it depends on the location of the node in the binary tree and also its own observation. For example, sensor 1 receives x1, yeah, this guy receives x2, and the subscript just represents the location of the tree. And consequently, the depth of the binary tree is n times k, and each path from the root to a leaf corresponds to a given transcript, just a given message to the centralized processor. And so the binary tree together with the A functions actually constitute a complete representation of the blackboard protocol, and we are only left with the statistical lower bound for finding a theta hat based on this strategy. And we can just do that by a very standard hypothesis testing argument. And finally, actually, we will arrive at a quantity we need to optimize. Surprisingly, this quantity is a geometric one. Let's say, let x be a random vector with independent and zero-sum entries. And our target is that given some t between 0 and 1, and given the probability of A is equals to t, we'd like to estimate to maximize the L2 norm of the conditional expectation of x given A. Note that this is actually a vector. So let's give you two examples. So let's suppose x is 2D, and for example, if A1 is something like this, actually we first consider the geometric center of this set, and then this is just the conditional expectation. So we'd like to find which A maximize the L2 Euclidean norm of the conditional expectation. So the results are different when we have different control on the tail of x. For example, if we only have the variance control, we have this inequality. You can see that the dependence on probability of A is actually linear. And if we have the sub-Gaussian tail of each xi, actually our dependence will be logarithmic. So it is because of the geometric inequalities that result in the different results for different score function. Okay, we'd like also to compare with the previous approach. In the past, people usually use some strong data processing inequality. This is one of the forms, for example, just present here for simplicity. So that is x is our observation, y is just the committed message. Yeah, we'd like to upper bound the mutual information between theta and y. That is the message between them. And now, And then theta to x is determined by the statistical model, and x to y is actually just subject to our commutation constraint. So this channel, theta to x, or this kernel, actually is fixed. And we can compute the strong data processing coefficient gamma star here. And this will lead to test result in Gaussian location model. Well, however, you can see that because usually we will upper bound the mutual information between x, y, y by k. So actually it will result in linear dependence on k. Whereas in some scenarios, we show that time dependence may be exponential, and this may also have not very clear operational meaning. OK, that concludes my talk. Thank you.
Okay, let's have a round of applause for all the speakers in the session.
Thank you.
And since we have an open problem session at 1:40, is it?